them, or do they just go off?
They just go off. You can just.
My only concern is I won't see this. Can I? Lights on, great, you know.
Let me know when you want to change the site.
We need to keep pressing it, unfortunately.
You just tell me, and I will change.
Tell you what we'll do.
Use it. And I both functions sometimes doesn't work.
Okay. Right. Are you ready to?
Not yet. Okay. I'm sharing with
Nothing comes through yet.
Yeah.
So as part of your course, do you get to go out and visit ships? As part of your studying, yeah, generally, have you been out visiting ships?
Yeah, I have been like on Calmac ships several times.
Oh, which one?
Argyle, Butte.
Oh, the smaller ones?
Yeah, smaller ones. Like
have you been to the larger one at Ardrossan, the Caledonian Isles?
no.
She's a bit bigger, a little bit older, but I think Argyle and Butte are a bit newer though, aren't they?
No, they're like small and like they weren't that new, I think.
Right, okay, because I know, I'm thinking of the two streakers they've got out of Gurek. They're a bit newer.
Yeah, they like, I think they're having two new ships.
Yeah.
New build ones, but I haven't been on that.
Yeah, previously they had what they called the streakers, and they had voice schneiders. Good system. An unusual system to learn to drive, but good system. I did a few years with Calmac as well, and it was on the bigger ships in the Western Isles. I'll give you a break. I'm going to get a heads up. So, no, that's quite interesting. And anybody else? Have you been out?
We have been board over several times as a cadet.
Ah, right, okay. So deck cadets or engineers? Ah, okay. I like to hear. They say oil and water can't mix, just add soap.
So we have CFC3.
Ah, right, okay.
And yes,
so, this shouldn't be new to you.
No.
You should know all this.
We should.
You should. You will. It's fairly low level stuff. The basic. Anybody else got any maritime experience?
Yeah.
Okay, so you're a deck officer as well?
I just got my brother.
Intelligence, that's why you're doing a PhD. Solving problems?
Maybe the problems.
No problem. Can I just get this right? Is this an LNG project? This is MoS LNG. Okay. Just when you mentioned Calmac, I know they're currently developing a couple of LNG fuel chips. I did quite a lot of work with Sigto, and obviously the new gas fuels. Quite an interesting topic. I don't know where we're going to find engineers to run these gas fuel chips. When you talk about cryogenic temperatures and the like, there isn't a lot of these guys around.
It's just dangerous still, but I hope it will.
I think it will work. And it's a step towards hydrogen and the like as well, which has to be good, so the more gas we can involve.
Well, it depends to like where oil price has decreased a lot recently, and with this price I don't think anybody will be willing to invest LNG as a big companies might do that, but I don't think.
Oh, obviously the Swedish companies they've started because they've got a very different mindset and much better. Okay, right. Right, okay. Give a brief introduction then. Okay. Obviously we've had a chat in here, so I've got a rough idea who the chats are. My name is Ian Brown. I'm a lecturer in college here. I predominantly teach Shipmaster's Business I teach meteorology, bridge watchkeeping, and maritime law occasionally, as and when they need any. My own background, I worked something called TK Shipping, which I'm sure many of you will be familiar with. That's who I did my training with. I sailed with them up to second officer, and I did a bit of management training in the office. I was there for a few years. I've also worked ashore with various other management companies, and more recently I spent 5 years working with a company called Witherby Publishing. Through Witherby Publishing, I did a bit of work with IMO because they the e-book reader and they do a lot of work with the library down there. I had Sigto and Orca. So I was involved in various working groups and other. Hence the reason I'm now here. And I'm here because the holidays are fantastic. Yeah, brilliant. It's almost as good as being at sea. What my intention today is just to briefly give you an overview of meteorology. Certainly from an officer's perspective, what we teach our cadets. Some of you I know are ex-deck officers, some of you are ex-seafarers. I don't know if there's any ex-marine engineers, but if there is any, that's really useful. Possibly more so given the nature of what we're discussing. And my intention is just to give you an appreciation. We'll look at the whole idea of where the meteorological cycles come from. We'll look at it from a global perspective initially, very briefly, some basic principles. Then we will come in and we'll start talking about the mid-latitude regions, which is where we are focused on, round about between 30 and 60 north, North Sea, Northwest Europe, this kind of area. And then what I'd like to do at that point is just give you an appreciation of how masters, officers interpret the weather. Everybody's seen weather forecasts, so hopefully. I don't anticipating it taking a few 2 hours, but please, if there aren't any questions, I know it's a presentation, and I'm a bit restricted because I know we've got people watching at the moment as well, so we can't have too interactive in terms of handouts. But if there is anything you want me to discuss, stop, go over, please do so. I'll try and keep it to the principles in Met as far as I can. Simple. There are a few handouts for those here. For those that aren't here, my apologies. Okay. Those are just a few handouts for the slides here. It's more a reminder if you want to jot anything down. It's not something that will be deeply assessed as part of it. You may find there's a few questions, but nothing major. Fairly basic. Okay. And for the ex-navigators, they'll be very, very straightforward. Okay. So just to start off, same as Jim Brown and it'll work. Okay, perhaps it won't. No. Purpose of meteorology? Avoid this. Okay, or not avoid purpose of meteorology, the purpose of forecasting. Seafarers, from our perspective, to avoid this. This was the MSC Napoli. MSC Napoli encountered bad weather, she broke down, and this was in the Dover Straits. Huge number of containers lost, massive salvage operation, high cost. So from an application point of view, end of important denying it. And again, quite useful, mid-latitudes between 30 and 60 degrees north. Okay. Another one, other side of the world, the Pasha Bulkar. I think the master was just trying to get ashore quickly and get home. That's taking shore leave one step too far. Yes, it's a nice beach, but much better to anchor up and go ashore. Okay? Again, bad weather caused that breakdown. I don't know if any of you are involved in Energy Efficiency Design Index, the EEDI. Certainly when I was down, I think it was MSC, certainly 2-3 years ago, we were talking about EEDI. And one of the big concerns was in bad weather, with ships where the propulsion system has been reduced to such an extent to be more environmentally compliant, would that have a potential knock-on effect? Those ships become underpowered in bad weather. They're only rated up to a Force 7 or a Force 8. Could this be more common? And so I remember there was a delegate from Greece who raised that floor in plenary. So, an interesting one, but part of the reason why we observe the weather. This ship here only happened 2 weeks ago. That's the Tokyo Spirit. Okay. The actual investigation is not yet completed, but looking at it there, I've got a funny feeling that weather or a breakdown of some description has been involved. The vessel has managed to get her anchor out. It doesn't appear to have hit the breakwater. So, a major problem. Another, just for those of you naval architects, one of the biggest things we find on ships, and ex-navigators, ex-engineers will probably know this, are the cables, the winches. Frequently they struggle when you're putting them out on a ship. These are massive ships. Just be aware of that. If we run it out too fast, it'll just pull the bitter end out and we'll lose the chain. So again, the weather's bad. We will use them as a final resort, but we as navigators are also very aware of the limitations of the equipment on board. And we also know ship owners will buy generally the minimum they need. They will not overpower things if they can avoid it. Okay. The previous ones were more financial, were more a concern. The Estonia, that was much, much more of a tragic event. Lots of people, just under 1,000 people. This was in bad weather. There's lots of conspiracy theories around it. That's why I'm here. That's not what's up. It's up there to show what can conceivably happen in bad weather. I've worked on ro-ro ferries as well, and obviously the big concern is ensuring your bow doors and stern doors are shut, all your systems work, everything absolutely in operation and it's done properly. This was a huge loss, horribly tragic. But what it does show us is why we need to take. So that's the reasons why we're talking about what we are today. I know this isn't LNG we're talking about, but the principles apply. LNG ships may well be much more structurally sound, and ship owners invest a lot of money in them because they are big investments, but it's still subject to the same external conditions. Okay. Right. I'm sure you recognise this thing. This is where we live. Okay. The world. I'm going to look at this from a global perspective initially. The world it rotates, it's subject to heat, and we have water. Those are the three driving factors. The heat, that changes. If the heat changes things. Different parts of the world has the heat, cloud cover, solar conditions from the sun, all these factors affect the weather patterns on the Earth, whether it be from El Nino off the coast of Peru in the Humboldt Current up to the North Pole. Okay, all these systems move up and down and follow the sun. And as a consequence, they affect our weather, both on a day-to-day basis but also on a weekly basis. Before I do that, let's talk a little bit about some of the simple principles. Some of you may have heard of the expression Coriolis, some of you may not. Some of you have played games like Call of Duty. You have to take into consideration Coriolis and the rotation of the Earth when you're playing your game. Others may have heard it in a previous training program. All Coriolis is, in effect, is the effect of the rotation of the sun, or rotation of the Earth, the movement of the Earth on fluids and air particles, and the wind on the Earth. That's all it is. Dead straightforward. Just to try and explain this, if we were to take a ball, a small ball, an object, take up to the North Pole, potentially the South Pole, but we'll talk about the North Pole for the moment, and if we were to throw that due south, if we were to throw that from the North Pole straight south, that will take us, or it will take a path similar to that, if you throw it fast enough. Not quite in orbit, same principle. Okay? If it was able to maintain a constant distance above the Earth, it would go around this way. So that's looking at it from the side. If we were to look at it from directly above, it would look like that. Okay? Yeah, these pictures are from Google Earth. But it works. So that was to come down there. If that object was to be thrown straight down, that's the path it would follow. It would follow that path if Earth didn't rotate. Okay. ball, that object is not fixed to the Earth. So underneath that ball, the Earth is going to rotate. So someone here on that patch of land there, if they were observing the ball when it was first thrown, it would be there. Then, as the Earth rotates, the observer will move across here. So obviously the Earth is beginning to move in this direction. That would ultimately give us a path for the ball, in this instance, the missile, projectile, we follow a path that would appear to curve round to the right. That's the apparent motion we're talking about. True motion, the ball is actually going in a straight line. Because the Earth is taken underneath, it appears to go to the right. Similarly, if you were to do a similar thing from the South Pole and throw it northwards, it would appear to go to the left. Ball quite straightforward?
Yeah.
I know you guys are, your abilities is far beyond this. I'm just trying to give you the basics. There's a video here, I'll let you have a look at it. It was produced, it's a couple of lectures, I think, on basically a roundabout, which is rotating round, and it's just to try and illustrate the point. I won't show you all of it, just to show you this whole concept of apparent motion. Hopefully, it should work. I hope. Excuse me. Right, these two chaps here, they're sitting on this contraption which is going round and round. And what they're going to do is they're just demonstrating this apparent motion idea. Okay, it is relatively simple, I appreciate that. Just bear with me. As you can see, no motion, the equivalent of a still Earth. And all they're doing at this point is throwing the ball back and forth. Once we start the rotation, and they've thrown the ball in a straight line, the ball appears, in this instance, to go to the left. This shouldn't go on too long, and as you can see, it's looking from above now. The balls are being thrown, and they appear to go to the left, or certainly to the observers they do. But as you can see, the ball is actually moving in a straight line. Yeah? So all we're showing here is how the rotation of the Earth changes your perspective. And as in this case, it appears to go to the right, taking the opposite direction. And that is exactly the same principle as Coriolis. Right, I think that's... Is everybody quite comfortable with this? Yeah. Okay. It's a bit like being back at school, I appreciate it. Okay. So Coriolis, as we say, the Earth is rotating. The projectile comes down here, gets deflected to the right. It appears to, according to the observer. If that was a wind, okay, or a fluid on an Earth, starts from this point here. It was to move south. That fluid, because the Earth, the solid bulk of the Earth underneath, is moving, it would appear to be deflected to the right. And that's what happens to winds. Any wind coming from the north, in this instance, would be deflected to the right. Any wind coming from the east would also be deflected to the right. In the southern hemisphere, they are always deflected to the left. That force we call Coriolis. Okay? We do need that for what we're about to discuss. Or look at, sorry. So that was Coriolis. We're all okay with that?
Yeah.
Good. Okay, similarly, if anyone else has any questions, please feel free to ask. So that's the movement of the Earth we're discussing. Next bit, everything starts from the sun. Okay. Everything in meteorology starts from the sun. It all starts from heat. What we're looking at here is the Earth, assuming the Earth wasn't to have a If the Earth wasn't tilted, and all I've done is divide it into bands. Okay? Each of these bands, North Pole, 30 degrees north, 30 degrees north, equator, 30 degrees south, 60 degrees south, and the South Pole, Antarctica. So if we can assume the sun's rays, the sun is much larger than the Earth, so the width of the rays hitting the Earth, I've assumed all going to be equal width. Just prove this point. Each of those rays, as they hit different parts of the Earth, the width of those rays, this what we call incoming solar radiation or insolation, comes from the sun and hits the Earth. So the width of, or the equivalent width of this ray here, as it strikes the Earth, would cover an area approximately that big. Okay? Fairly intense, almost at 90 degrees, almost perpendicular. However, at the poles, the same width, sunlight hitting the Earth, would be spread over a much, much wider area, because the Earth is angled almost, this area it's almost parallel to it at this point. So the actual amount of heating striking the poles is much less. There's much less incoming solar radiation, much less heat. You can add to that, as it cools down, we then get the ice caps. The ice caps are white, and as a consequence, they also reflect heat. So the cooling effect here and here is much, much greater. So that ties in with global warming, and so the warmer the Earth gets, the less the ice caps, and it becomes a vicious cycle. But all we're looking at here is the intensity of the insolation as it hits the surface. Now, as the surface heats up, it then heats up the air in contact with it. Okay? So as that air heats up, I don't know your knowledge of physics, I'm assuming, given you're all naval architects, that would be good. Some of you may not be, but hopefully your physics is decent. At this point, it'll heat by conduction. The Earth heats up the air by conduction. The air in contact then heats up. Hot air will rise. As it rises, it convects upwards, convection. And as it rises, the air fans and it cools. EV over T, adiabatic cooling we call it. Volume increases, obviously temperature drops. But what actually happens is that air rises, it leaves behind a gap, a lower pressure. Okay, so at this point it rises and it leaves behind a lower pressure here. At the poles, they're much cooler. Cold air, dense, heavy, and it falls. So what we end up with is a high pressure sitting on top of the Earth, near the surface. High pressure here, low pressure, high pressure. Okay, this is how our winds start. And what we actually get is this banding system at different points. If anyone's been to the Azores at any point, 30 degrees north, nice big area, high pressure, brilliant place to go for holiday and vacation. Fantastic. Nice calm area, brilliant place. 60 degrees north, the Shetland Islands, the Faroe Islands, not such a nice place to go on holiday. Okay. Low pressure, it draws air in from elsewhere. Okay, not fantastic. That said, Norway and Sweden are nice, tend to be a bit more stable. But they tend to be a little bit above this low pressure. So, when we look at these pressure systems, what we'll find is we get air rising and falling in different points. If we talk about a gradient, okay, I'll have to try and figure this one out. If we had a gradient is a slope. We have a high end here and a low end down there. Put anything on the high end, it will flow to the low end. The steeper the gradient, faster the flow. What we get here is the equivalent of a high end, a high pressure system. Here we have a low pressure system. So the air will flow from the high end of the gradient to the low end of the gradient. Pressure, gradient, force. Chiasm, high pressure and low pressure. And that's what drives our winds. Okay. So what we get there, high pressure, and it flows from high to low, flows down towards the equator. This one flows north, and this one flows. And that creates these convection cells. We call this a Hadley referral. You don't need to worry too much about that. Creates convection cells on the Earth. Now, we spoke briefly about Coriolis. Well, we didn't speak briefly, we spoke quite a lot. As this air, remember we said it flows from north, south, from high to low. The Earth is rotating underneath, so it deflects to the right. This one deflects left. And we get this effect all over the Earth. Some of you may remember this. High to low, low triangle. Obviously in this part of the world, near just south of the polar front here, low pressure system, we get westerlies. The UK, North Sea, is around here. We get all this weather coming from the west. Back several hundred years ago, when sailing ships were carrying out their trade, they would use these winds. The Europeans would travel from Northern Europe or Western Europe down towards the trade winds, past the Canaries, and they would use these winds to take them across to the Caribbean. And those were known as the trade winds. For that reason. And then when they came back, they used these westerly winds. Now that was their trading pattern. This helps us as navigators. We use these winds. The currents follow a similar pattern as well. Everyone okay with this? There are a few other things that might be of interest. It might not. This area here at low pressure, there's almost no wind. That's known as the doldrums. Okay? The doldrums, if those of you that know, in English when we talk about someone being in the doldrums, it means they're low, they're depressed feeling, they're down. And that's where the expression comes from, the doldrums. Because when a ship got stuck there, they couldn't go anywhere. This area here, this high pressure where the Azores were, fantastic area, but for a sailing ship, treacherous, because there's very little wind. And those became known as the horse latitude. At that point, to reduce weight, they could get rid of the horses. And that's where the horse latitude comes from. With these expressions. Lots and lots of what we talk about generally comes from our maritime heritage. Okay. Some of the other ones I'm not going over today because they're not. Okay. In addition to the winds, as navigators, we've got to be aware of currents. Okay. The world is split into different regions, and remember we said anything which wasn't fixed to the Earth travelling south would be deflected to the right. So we can see the effects, Coriolis. There's other effects involved here as well. The rotation of the Earth causes a lag. But we can see here this circular motion. Okay, it's gyroscopic, rotational. That's known as a gyre. The navigators use these. We use them when we're planning our passages. We use them when we're doing route planning. Because if we follow the currents, we follow the wind patterns, we can reduce the amount of bunkers we're consuming, the amount of fuel we're using. If we go against it, it becomes a big problem. And these gyres, as you can see, this one's deflecting to the right, one deflects to the left, so on and so forth. All the way around. So these currents. Some you may be familiar with, the Canary current, the Gulf Stream obviously has a huge effect on the heating of the northwestern Europe, particularly on Scotland. If we travel a bit further north, we have palm trees in certain areas because we don't get much frost, and that is entirely due to the Gulf Stream and this drift upwards. It keeps us at a much, much more temperate level. Our climate is very, very different to North Canada and Alaska, even though our latitude is the same. We don't have glaciers. The Alaskans definitely have glaciers. And it's entirely due, or not, predominantly due to the Gulf Stream and these warm airs coming. Okay, I feel as though I'm talking at you rather than with you. Does this all make sense?
Yes.
Don't just sit and nod either. Guys. And you can see we also have anybody that's seen Finding Nemo? Mm-hmm. Yeah, East Australian Current, the EAC. Okay, don't burst into the song, but show you. And it's the combination of these nutrients coming down here, combined with the region and obviously the Great Barrier Reef, which makes it such a diverse area. and it's coming under increasing protection, which is good. We also have other currents, like the Agulhas coming down here, and the South Atlantic coming across here, which is sometimes called the Roaring Forties. Where they meet, this is a fairly treacherous area, if anyone's ever navigating down there, because where this current meets this current, and the waves can cause a doubling of wave, and, well, I wouldn't say they're common, you can have rogue waves, freak waves, where the wave amplitude builds up, and that can cause very steep, dangerous waves. Similar down off the coast of Argentina, south towards the Falkland Islands as well. The North Sea, one of the biggest problems in the North Sea is obviously the shallowness and the steepness of the waves. They're rolling in. And many of it, and I've certainly sailed out there. I'm sure some other people may have been out in that area before. Have any of you been out in the North Sea previously? Yeah. Fantastic in the summer. Horrible in the winter. If you can sleep in a roller coaster, you can sleep in the North Sea. Okay. The only place I've ever literally been lifted out of bed and landed on the floor. I was sleeping. It wasn't very nice. But the other big problem you have out here in the winter is the darkness. Once you're above 465, it never fully gets light. In some places it stays permanently dark due to the angle there. And all these things add to the other problems you as naval architects, students are going to have to encounter and take into consideration. Particularly if you're dealing with things like ergonomics, safety, design, all part and parcel. This region here is quite interesting as well, but we'll come to that. I'm sure everybody's aware of tides, not really a meteorological issue. I just figured I'd mention it just to try and keep, because some people get currents and tidal currents mixed up. Currents, where, as we discussed before, tidal currents change on a daily basis. Tidal currents are based on the moon and the sun, and their gravitational pull on the waters of the earth. When they're in opposition, it pulls it away. If the sun and moon were what we call in quadrature, tend to get a bulge in this direction. And obviously the moon rotates every 28 days, sun every 365 and quarter, I think. I can't remember exactly, 0.25 something. Okay? So, tidal stream is slightly different. It's important, because if you're operating in shallow waters, something you need to be aware of. As navigators, I'm sure you absolutely are. You'll have done hundreds of calculations on this. Yeah. Obviously, over and above just these effects, you may also have to take into consideration the shape of the land, the geography around it. It's going to disrupt the flow of water. Some areas it will localise it. Some areas it will create huge tidal streams. There's a place in the west coast of Scotland called Corryvreckan, where we can get tidal streams in excess of 12 knots. Very, very fast. They've got large whirlpools in the area, and if they pull anything down, they won't surface for a couple of miles. And they change direction a couple of times a day depending on where the sun and moon are. Other areas where maybe 8 or 9 knots, it's enough to make a buoy which is attached, one of these floating buoys, it's enough to make those submerge, sheer force of the water. And as someone who's tried to take ships alongside in those streams, it makes it quite difficult. Because as you get close, the stream lessens. So you're always working your engines. So manoeuvrability in that situation is very, very useful. And that is purely down to tidal. It can have a huge effect on your ships. The other issue which can have is weather, pressure system. If you have a very high pressure system on a good day, lots of sunshine, it builds up, it will actually press sea level down further. A high pressure system will reduce it. So if you have a very low tide, the sun and moon in opposition or pulling the same direction, you've got a very high pressure system and a good flow of water, you can take that below what you would expect to see as predicted. Okay? If you've not had a lot of rain as well, it all reduces it. So if you're operating ships or planning to operate ships, shallow waters, be aware of the tidal effects. It's not strictly speaking weather, but it's affected by the weather, and it's very important. There's lots and lots of navigators who have miscalculated tides, they've taken out bridges, ran aground, created large pollution incidents, been stuck in port for several weeks because the ship has gone deeper than anticipated and then the suction holds it in place. And unfortunately you're not supposed to shuffle the ship off, although it might take some of the barnacle and the fouling off, it also takes the paint off. Yes, you've got to get off to get. So just be aware that it's tidal effects. So we've mentioned the wind, Coriolis, normal patterns. We've mentioned currents, and we've also mentioned the tide. Again, we're just principles I'm looking at. What I'm now going to look at, very, not in too much detail, is waves and the differences. These are, I assume in your studies you've done quite a lot of work on waves and how they affect ships. The shapes of wave you work on are probably the tricoidal or sinusoidal. Which one do you tend to work on, these swell waves, or do you work on tricoidal sea waves?
Almost one.
Yeah, the swell will be kind of sine waves.
Yeah.
Okay. I don't know how easy it is in models to actually show the effect of winds and how ships will react, but it's obviously very, very different. The way in which a ship reacts in a wind wave compared to a swell wave is massive. I'll just give you a rough idea of the difference of the two. What you're actually looking at here is a tropical revolving storm. Okay, it's nice and clear, you can see exactly where it is. In the middle there you can see the eye of the hurricane. And round about, you can see the rotation of how it's funneling in like a giant Dyson, a giant cyclone. That's what you're looking at there. There's getting drawn in and pulled up in the middle. You can see there. You get different types of wave associated with this. In the storm itself, we have these sea waves. Okay? Sea waves happen where the wind happens. The wind is local and the wind is blowing. We get this tricoidal shape, which is steep. On the top, it tends to be quite sharp. That's caused by the wind blowing this way, and the pressure exerted here, and the lower pressure there, causes this apparent movement of water. It's no different to a sound wave. It's not actually travelling, it appears to be travelling. The movement of the wave will tend to move in a specific direction. You can see here, the wind is blowing towards, and as it's blowing away, and as you can see, it's breaking at the top and we're getting these long streaks behind. That's a local wave, it's a wind wave. Wind waves tend to be steeper, they're very uncomfortable on a ship, and they put the ship under more strain. The ship tends to slam, bash around more, they're uncomfortable, certainly from a safety perspective. It will affect fatigue, because you can't sleep. Some ships, they don't have chairs on the bridge, which is fine on a nice day, but when the weather's bad and you're getting thrown about and you're having to stand there for between 4 and 6 hours at a time, exceptionally tiring. Very, very tiring. And when the weather's like this, it's hard during the day when you can see the waves. At night time, you can't see the direction it's coming from. And you may have waves from different directions. And then trying to predict it is very, very difficult. And the ship will, they don't just move up and down or side to side, they tend to move around and loll about. Okay? They'll dip in and out of the waves. Navigators will, if the weather's too bad, they will go bow in, slow right down, and just maintain speed as possible. The weather isn't that bad, it's now taken so it increases in the movement over. Okay. It's all about how we approach. It's like an angle of attack. If you get it at the right angle, it makes life much simpler, much more pleasant for the people on board. So, sea waves. Tricoidal, sharp, difficult. Those will be in the storm itself, where the wind is. However, further away from the storm, we get this massive ripple effect. Okay? We get these huge swell waves, long waves, and these tend to be sinusoidal sine wave. Large, smooth waves. Okay? They can be very deep, they can be over 100 meters long. Massive waves, these large sine waves, these swell waves. but equally difficult, because very often in the middle of this storm here, you'll have sea waves and you'll have swell waves coming in as well, which makes it difficult for a ship to react. Difficult to master. So that's two different types of waves. Again, you drop the penny in there, and this is a ripple effect here. Right. We've kind of spoke a little bit about principles, and I've given you the basics. What I'm going to talk about briefly is a few different areas here. I don't know if anybody here who was at sea has been out in the Arabian Sea, the Indian Ocean, Bay of Bengal. Okay, what time of year were you there?
Summer? Summertime?
What time in summer?
June and July.
Okay, so July.
Yeah.
The weather was beginning to pick up.
Yeah.
We have monsoons. Okay, monsoon is it's derived from the from season. You have a wet monsoon and you have a dry monsoon. Different times of the year. Northeast is dry. Southwest is wet. That is definitely the wet. Okay, this lasts for a couple of months. Constant. When ships, oil tankers going to the Persian Gulf, coming from the Far East, normally they'll come down in ballast. When a ship's in ballast, it doesn't have a lot of weight in it. It's nice and high out of the water. And as a consequence, it acts like a cork. It just tends to bob around. When you're heading in this northwesterly direction, you have what we call the southwest monsoon, where these winds come up from the Indian Ocean and they take the ship on the port side, and it causes the ship to roll. This can be ordinarily, it will set a force 7 or force 8 gale. Strong winds. And because it's blowing for such a long time, you get this big swell wave growing as well. The waves continue, the wind continues, very uncomfortable on a ship in ballast. Certainly for a ship like an LNG tanker, you have to make sure enough weight is down in the ship, otherwise it actually gets dangerous. I've worked on double hull VLCCs in this region, going back and forth between Japan and the Persian Gulf. And when you're in ballast, the ship is maybe rolling 15 degrees one side to the other, sometimes more. This ship is maybe 30 metres from the waterline up to the bridge, so it's a big distance, standing static for this to actually roll through. Okay. It's dangerous because it puts strain on other equipment on the ship. Anything tied down is problematic. Any equipment on the ship needs to be well fastened down, and it also makes it difficult to eat your soup. It's like the North Sea, but on a much bigger scale. Floor so you can sleep, but still difficult. At that point, it's much better to be in the engine room, because you're much closer to the centre of gravity, the higher up you are, the worse it is. So for the master, very uncomfortable. So that's the price of power. So in that region, down near the tropics, we have these monsoons. Okay. There's monsoons off Africa, but they tend to be a dry monsoon, and then obviously a more wet monsoon in the summer months, West Africa and Nigeria. But the most prevalent one and the best known is that in the Bay of Bengal, the Arabian Sea and the Indian Ocean. It does have a big effect. We also have, in the polar regions, ice. Ice is a major hazard for navigators. Ask the captain of the Titanic. Major problem for navigators. It doesn't reflect radar very well. Okay? It's not 90 degrees, it's rugged, it reflects radar everywhere. So you get if you do get any reflection from a radar, then a return echo, it usually looks much smaller than it is, and it will disappear and come back. Small boats do. It's hard to see. Ice is a big problem. Also, it's difficult to see at night. Okay? Unless it's a very bright night, it's hard to see. Another big problem with ice related to fog. We'll come to that in a second. One of the biggest issues with ice that people often forget is 80% of an iceberg sits below under the, and they can be incredibly dense, and it will just rip through steel hulls. Even ice class ships, depending on the classification that they have, Ice class ships, generally icebreakers, are designed to go in at slow speed. Most of them will either go stern to up and brake, or go forward up, and then they'll break down if the ice is thick. That's my understanding. I've never sailed one. You guys are the experts in naval architecture, so you'd have a better idea than I would, but that's my understanding from the ice pilots. But yeah, ice is a major issue. Major problem. The other big issue with ice is, in certain areas of the world, quite often there's a lot of marine life around areas where there's ice. Certainly in places like the Grand Banks, the east coast of Canada, Labrador, a lot of fish around there, consequently fishermen. Fishermen and ice, two difficult things from a navigator. Okay? Lots of friends who are fishermen, but they all agree. Okay? Fishermen obviously have certain things they're trying to do, and navigators and merchant ships are also trying to do the same. In other areas of the world, certainly the warmer areas, hurricanes, tropical revolving storms, otherwise known as typhoons, cyclones, or in parts of Australia, the Willy Willies. Okay? Hurricanes. Hurricanes are very intense storms. They grow very quickly, and they are very, very dangerous. Not just the wind speed, not just the sea surface, it causes that when they hit the coast, pull the air up above it, or the water level up above it, and acts like a large vacuum, and they push it ahead. So when it strikes the coast, coastal areas, that storm surge causes massive damage. So ships, when they're in port, if a hurricane's approaching, will go out to sea. They don't want to be stuck in port because there's nothing they can do to get out of the way. Certainly the most intense. Hurricanes are so intense, we talk about hurricane force winds, which is what we get in the North Atlantic. We don't get hurricanes, we get force. Hurricanes also have their own scale, the Saffir-Simpson scale. It categorises it from 1, 2, 3, 4 and 5. 5 being over 155 knots. 155 miles or so. And they are incredibly devastating. And they're also very, very unpredictable. Hurricanes tend to be nearer the equator. They do travel north, but as they travel north, they begin to lessen. And the last one, which we get almost everywhere, fog. Fog is a big problem. Fog is a big problem for navigators. Electronic equipment is very useful, it's very helpful. And for ships which perhaps in the future may not have navigators on board, radar doesn't pick everything up. Okay. So we need to visually see things. As navigators, our eyes are our key. So whether they plan on ships without crew on board them, maybe to put some form of video monitoring system, I don't know. But certainly we rely very heavily on our eyes. It's what we trust, both for position fixing and for collision avoidance. Fog is a problem. Rain is worse because rain affects visibility and affects radar. Rain attenuates radar, it disperses it, it deflects. Fog, at least, it doesn't get affected by rain, or doesn't get affected. Radar doesn't get affected by the fog or water. However, one of the problems we do have, frequently where we get ice and we get fog, we often get fog. Areas like the Grand Banks of Newfoundland, the North Atlantic to the west, where the warm air coming up, pushed up by the Gulf Stream, remember we discussed these westerlies coming up? We also have cold water coming down from Greenland, bringing the glaciers. When you get a really cold surface, and you get warm, wet air, in between you get a layer of condensation. Fog. Okay. So that area is particularly dangerous if any of you are out planning on taking ships out there at any point, because around that area you get glaciers, very large ones. That's where the Titanic was sunk. We've got fog, and we've got a warm current and a cold current meeting, huge amount of nutrients, lots of fish, lots of cod. So what we get in that area is a very dangerous area. Right. So what my intention is to do is to have a look at middle latitudes. If you want to take a 5-minute break, are you comfortable? Because I've got roughly another 40 minutes or so. And it's quite hard listening to me talk for 2 hours, so if you want to take a 5-minute break.
Please tell me now. 5 minutes.
Yeah, is that okay?
Yep.
Okay. Right.